Thank you. Thank you. So nice to see so many familiar faces, good friends. Thank you for coming tonight. I wrote the first book in 2001, and any book on the brain is outdated almost as soon as you've written it. So I began to look at what's new out there. And while the second edition is much like the first in many, and we'll cover some of the basic stuff that we're learning about the brain, I became really interested in the impact of sleep on learning a lot about the impact of sleep on exercise. In fact, I'm doing workshops now on how to delay the onset of Alzheimer's. And I'll just give you a hint right now that the #1 research finding for delaying the onset of Alzheimer's, even if you're genetically programmed for it, is exercise. And you'll see why when we talk about the brain here in a minute. So I added also on the impact of technology. You know, I don't know if any one of you, you know how these things come through in emails, you get all of these. And one came to me the other day on this little old lady, my age, who was at the grocery store, and she didn't have a bag, you know. And the grocer said to her, the fellow checking her out said, "Well, we're really green." And she says, "I'm sorry, I'm not green." And they went back and looked, you know, if you look at early life, we walked to school. The television, which we got in my home when I was 14, the first one was this big, black and white. No one in any of my high school or university classes taught me how to get spam off my computer. We didn't have them, you know. And so if you go back and look at the life, you know, that I lived earlier, it was very green because we didn't have all the technology. Well, since we know a lot about how the brain is shaped by its environment, obviously technology is going to shape the brain. And we'll find out that that's either positive or negative. And the other thing that's not even included tonight, if I have time, I'd like to talk for a minute about, I did just a 15-minute presentation for the teachers at Napa Valley Language Academy today, where my grandchildren go, on rethinking praise and how much of what we think about as praise is really counterproductive. So remind me toward the end, if we have some time, I'd like to just share 2 or 3 things that the research is showing about what ineffective and effective praise is. But let's start with how the brain works. This is all we knew about the brain 30 years ago. This is a brand new field, neuroscience or brain research. And the reason that we didn't know much about the brain, you know, we knew a lot about what was going on in the heart. They were doing open heart surgery. They were transplanting livers from one person to another and kidneys from one person to another. At the same time, they were still doing frontal lobotomies. You know what a frontal lobotomy is? You probably don't want to know, but I'm going to tell you. They did some research on monkeys and found out that they had these violent monkeys, okay? And if they would mess up the frontal lobes of the monkeys, they weren't violent anymore. So they decided to try it on people. We did 150,000 of them in the US. And and I'm not going to tell you how they did it because you're eating, but they put a probe into the brain and just scrambled the frontal lobes of the brain. And sure enough, these are people who had been previously in mental institutions who were extremely violent. They weren't violent anymore. Did you see One Flew Over the Cuckoo's Nest? Yes. That's a very good indication if you saw what Jack Nicholson was like before and after his frontal lobotomy. That's exactly what happened. The Kennedys had a daughter that they had a frontal lobotomy done on. I mean, really primitive, and so, you know, of course they weren't people anymore either. They were just like zombies. All right. But that was happening at the same time where we had all this technology of how to do a bypass in a heart. So that's how far behind the brain research has been. And I'll show you why we've moved very, very rapidly in the last 20 years. So this picture was as good as any picture, you know. We didn't know how the brain worked. So people made up things, okay? And we believed them. And we still believe them. I call them neuromyths, myths about the mind. Have you heard that you only use 10% of your brain? That's not true. Have you heard that listening to Mozart will make you smarter? It will not. It will not. No, no, absolutely. The research is very flawed. My favorite. Have you heard that every drink of alcohol kills 50,000 brain cells? Well, you just tell me, how would they know that? There would be no way to test that. You can't open up the brain, count brain cells, drink alcohol, and then see how many died. You know, it's and we believe that. And I think we made it up to tell kids to try and keep them from drinking, and it doesn't work, you know. Now, let me give a caveat here. It doesn't kill brain cells in your brain. It does in the fetus. All right, women who drink, especially who drink heavily when they're carrying a child, it's called fetal alcohol syndrome. The severe profound retardation is the leading preventable cause of mental retardation in the US today. We still have doctors telling women it's okay to drink. It is not. Why would you take that chance? All right. There's another period where alcohol appears to be, or the brain of a particular age appears to be more vulnerable to alcohol and drugs than any other age. It's not you. Do you have any idea what age that is? Adolescence. So some of the research is showing that the adolescent brain, and do you know what the age of adolescence is? It is 11 or 12 to 25. Yeah. And we have been assuming that at 21 they're old enough to vote, and at 16 they're old enough to drive. And what we know, and which is another workshop, is that the adolescent brain is not complete. You do not have a functioning adult brain until around 25. So there's some problems there, and this is why alcohol and drugs appear to be more of a problem at adolescence, because the brain isn't done, and they interfere with the final, putting together the brain. So we had these neuro myths about the brain, and people believe them because we are not good consumers of research. We read things in the paper and believe it, all right? And quite often the articles you see in the news media and in popular magazines didn't read the research well. So this is your brain. This is an actual photograph of a human brain. This happens to be, obviously, an autopsied brain, which was the only way you could study a brain until a few years ago, all right? And unfortunately, looking at an autopsy brain doesn't tell you a lot. I don't know whose brain this is. I do know it's a female brain because it's a photograph of a model of a brain I have that's a female brain. You can't tell much by looking at this brain. You don't know whether you can't tell by just looking. Is this a male or a female brain? You can't tell how intelligent this person was. You can't tell whether this is a person who had autism, ADHD. You can't tell whether it was an artist, a musician. You can't tell whether this is a person who had trouble with math or maybe was dyslexic. So autopsy brains didn't help us much. Plus, an autopsy brain is very, very different in many ways than the brain you have in your head right now. I don't know if any of you have ever held a brain, like a sheep brain or a cat brain or something in your biology classes. It's kind of spongy, sort of solid. In your head right now, it's not that consistency at all. It's more like the consistency of tofu in water. It's very mushy, very mushy. And and the reason for that is at the moment of death, all of the blood and all of the fluids drain out of the brain, and you have this kind of a solid substance. Now, autopsy is only helping us in one area today to diagnose something. Do you have any idea what that is? Alzheimer's. Alzheimer's. Because in Alzheimer's, we're going to take a look at brain cells, and you have brain cells making connections, and in Alzheimer's, a plaque tangles develop on some of the connections, and you lose the ability to make the connection, you lose the memory. Well, those plaques and tangles are visible under a high-powered microscope. So you can tell what stage, if the person had Alzheimer's or not, and what stage they had. So they will take very thin slices of human brain after autopsy, put it underneath a high-powered microscope, and they can tell you this person had Alzheimer's, and they were a 1, 2, 3, 4, 5, or stage 6. All right, which is not terribly helpful, okay? This brain is covered with a very thin layer, about 1/4 of an inch thick, and this layer is called the cortex. And in Latin, everything in the brain is named in Latin, for some, or Greek, means bark, or neocortex means new bark. Anyone have any idea why that cortex, that outside covering, just like a tree has bark, your brain has this covering, have any idea why it is so wrinkled? Someone said the other day because it's been in fluid. Not the right answer. Okay. To give more surface area. You're right. You're right. Because what happens is as the brain is developing in utero, in the womb, by about 6 months, the baby has developed up to 6 months, the brain's only about this big. And in the last 3 months, it grows tremendously, as does the rest of the body of that fetus. But the problem is the brain grows and grows and grows, but the skull is only this big. Okay, and you don't want it any bigger, let me tell you. So what that little brain has to do is fold in on itself, and that's why a brain is folded, to give more surface area. If you took the cortex off your brain today, okay, and spread it out, could smooth it out, which you can't, but if you could, until it was smooth, it'd be about this big. So it's a really good thing that it can fold to fit inside the skull, or you can carry your head around in a wheelbarrow in front of you. Okay? Okay, now in this one, what they've done is they took human brains, the person died, donated their brain to science, and they injected all of the blood vessels that normally had blood in them, but the blood has drained out. They immediately inject it with a red vinyl substance, and then they dissolved away the rest of the brain. So what you have here, and I love this, this is amazing, this is a picture of all the blood vessels in your brain. This is the most intricate blood system or vascular system in the entire body except for your liver. Now, why on earth do you need all of those blood vessels up there? Okay, why do you have more blood vessels in your brain than in your hand, your arm, your knee, your stomach, anywhere else? Well, the reason is that while the brain is not the largest organ in the body, your skin weighs twice as much as your brain. Your brain only weighs around 3 pounds, all right? While it's not the biggest organ in the body, it is the greediest organ in the body. At rest, where you are right now, because I haven't asked you to do anything too hard yet. Your brain is using 10 times more oxygen than any other part of your body. This is an oxygen-greedy organ. And if you deprive brain cells of oxygen for even a few minutes, they die. It's called a stroke. If you deprive a brain cell of oxygen, it dies. It must have oxygen. As it says here, you can go 30 days without food. You can go a week without water. You can go 4 to 5 minutes at the outside without oxygen, without suffering severe brain damage. Okay? Can you think of any health issue here? Knowing that your brain must have oxygen, and without oxygen, it doesn't work very well?
Napa County has the first or second worst rate of asthma in the state of California.
Okay, so air quality could have something to do with it? You bet. What else? Smoking? I'm thinking of something positive you could do. How about exercising? You see, if you don't have a good cardiovascular system, because, okay, let me back up. How does the oxygen get up to the brain? The brain doesn't produce oxygen. Where is oxygen produced? In the lungs. So how does that oxygen get up to the brain? Okay, take 2 fingers and put them very gently on either side of your windpipe. Gently. You should feel what? Pulse. What is that? That's your heart beating and sending oxygen up to your brain. Well, if you don't have a good heartbeat, a good cardiovascular system, you limit the amount of oxygen you get to your brain, and your brain doesn't work as well. So as I travel around and I see schools, and this was in the front page of the paper, Napa Valley Unified is cutting out what? PE and music. Yeah, I understand, the financial constraints. I understand the need for literacy and math literacy. I understand that. But I think that when you cut out PE and recess in schools, you're shooting yourself in the foot, because the brain doesn't work well without a good cardiovascular system. Unfortunately, they didn't ask me what I thought. Okay, second thing your brain needs, besides oxygen, its energy source is a simple sugar called glucose. All right? And where is glucose produced? In the liver. Right. And it's produced, glucose, it sounds like simple sugar, good, we should eat lots of sweets. No. It's from a well-balanced diet. All right? So now the liver's producing the glucose. Your brain uses 25% of all the energy that is produced by your body. Greedy, greedy, greedy. How does that glucose get up to the brain? Same way. Same way. Okay, here's another health issue. What if you eat a diet that is, are you turning the air conditioning down just a little bit? Good. I don't want people freezing in front of me. If you eat a diet that's too high in cholesterol, trans fats, what will happen to these two main ways to get oxygen and glucose up to your brain? They're called the carotid arteries, two big ones right here. What's going to happen to them? With something we call plaque, okay? And what if a little piece of plaque breaks off? Okay, look here. This is that carotid artery right here. See that big thing right here? Can you see it? Okay, that's this artery right here, leading up. It's feeding all of the blood vessels in the brain. That's the only way you have to get oxygen and glucose up there, all right? And if that gets clogged with plaque, you don't get as much oxygen and glucose. And then what if a little piece of plaque breaks off? It's going to get recarried. Okay, so watch. I'm going to take a little piece of plaque. And it's going to go up here. These are big blood vessels here. And it doesn't have any trouble getting through there. And then it gets up here, and the blood vessels get smaller and smaller and smaller. It gets stuck right there. And all of those cells right there die. Happens to be the speech area of the brain, and you lose speech. That's a stroke. Okay? So, all those things you've been hearing about that are good for your heart, they're good for your brain as well. Right? Okay. Now, back in the 80s, and this is ancient history and brain research, they discovered that you could inject radioactive glucose into your bloodstream. So you're going to take little molecules of sugar water. You're going to tag those molecules with the radioactive tag, about the same amount of radioactivity as a chest x-ray. I'm going to inject it into your bloodstream. I'm going to put you in a scanner. Because up to this point, we didn't know what was going on inside of the brain. What part of your brain allows you to see? What part of your brain allows you to hear? What part of your brain do you use when you're solving problems? What about emotion? What part of the brain controls whether you're happy or sad or angry? I didn't know any of that, all right? So what they're going to try and do is they're going to inject radioactive glucose into your bloodstream, put you in a scanner, ask you to do something, and see which part of the brain is working the hardest, which part is using up the most glucose. Make sense? It's called a PET scan, and that's what you're seeing right here. Now, on a PET scan, you will see there's a white line drawn around here to show us where the brain is. Because a PET scan does not show all those wrinkles, all the structures of the brain. It just shows what part of the brain's working. So this could be you. You're conscious, got radioactive glucose in your bloodstream. And in this one, they ask you to passively view words. They're just going to show you words while you're in the scanner. What they're looking for is what part of your brain controls vision. and they find it's the back part of the brain, right here, yeah, right back here. Okay? This is why when you bump the back of your head, you see stars. You have disrupted the visual system. Okay? Now you're still in the scanner. We're going to change the activity. Ask you to listen to some words. And you will find that a different part of your brain controls hearing, taking in auditory information. It's on the sides of the brain. Okay? Okay, let's change again. Let's ask you to do a little work here. I'm going to ask you to generate some verbs. Okay? I'm going to give you a noun, and I want you to give me a verb that you associate with that noun. Okay? So if I say broom, you would say? Car.
Dry.
Cake.
Eat.
My generation said bake. Times do change. Okay. Now, how did you know what to say? How'd you know what to say? How'd your brain let you know? When I said car, you all said drive. How do you know that? You've either driven a car or you've watched someone driving a car. That's an association that you've stored in your brain up in these two huge frontal lobes right here. This is an amazing part of your brain. This is a part of your brain that allows you to think, to do all higher level thinking. And it's the part of your brain that allows you to think about what you're thinking, called consciousness. You're aware, this is what I'm thinking, this is how I feel. Consciousness, probably which separates us from animals. All animals have emotion. If any of you have a dog or a cat, you know that they get sad or happy or angry, okay? The big difference probably between animals and us is that we're aware of those emotions. You know, my dog, when I leave, gets really unhappy, sees me packing, but he does not say to himself, she always comes back. You know, I just need to control my anger. Okay, all right. All right. This is the part of the brain that has allowed us to build cathedrals, to compose symphonies, to enjoy listening to them, to cry at movies. Right? This is an amazing. It's why you wear a helmet. Don't mess with this part of your brain. Okay, this is really important. All your higher level thinking. And this one is really interesting. This is a strip of tissue that goes from ear to ear, kind of like you have on a headband. With the difference is that you know you have two hemispheres? Oh, that's the other neuromyth. There are right brain people and left brain people. Have you ever heard that? Yeah. There is no such thing as a right brain person or a left brain person, unless they've had a hemispherectomy. That means they've had one hemisphere removed. Yeah. I'll tell you the reason for that is that you do have two hemispheres, and they're specialized. Language for most of us is in the left hemisphere. The left hemisphere is more linear. A lot of your reading takes place, for the most part, for most people in the left hemisphere. The right hemisphere is more global, gets the big picture. The left hemisphere gets all the details. Well, so we say a person who gets all the details is left-brained. Well, that's not true. Okay, that's where it came from. All right. So this headband, okay, this strip of tissue is going to go from one ear up over and down in between the two hemispheres, back up and over again. Okay, it is called the motor cortex. Motor cortex. What do you think it controls? Movement. All movement. So your ability to move any part of your body is controlled by your brain, by this strip of tissue going up over the top of your brain and back down. So I can tell you right now, I'm wiggling fingers on my right hand. I can tell you that a part of that motor cortex right here, the cells are firing right here. Because you do know that the left side of your brain controls the right side of your body and vice versa. Okay, these cells are firing and sending a message down the spinal cord, crossing over, hooking into the muscles in my arm to allow me to move them. If I raise and lower my left knee, I can tell you that my ability to do that right now, what's going on in my brain, cells are firing right up here in the right hemisphere, sending a message all the way down to the end of the spinal cord, crossing over, hooking into the muscles, and allowing them to contract and expand. You all know what happens if you disrupt that in some way. If you have an accident, you damage all of those messages going from the brain down. What happens? Paralysis. Nothing wrong with the muscles, but the message can't get from the brain to the muscles. And one of the biggest areas of research right now is how do you repair those fractures to the spinal cord? And they're having some success with rats at this point. And incidentally, you need to know that mammal brains are all pretty much the same. All right? A rat brain is just like a human brain. It's a lot smaller, okay? Doesn't have the ability to consciousness and a lot of other things. But the basic working and the basic structures in all mammal brains are the same. So the study of animals is really helping us to understand. You know, they can create rats and mice with disease, a whole strain of them. All right. So, for example, they can create autistic mice. They can create mice with Alzheimer's. They can create mice with Parkinson's. All right. And they get a whole strain because it doesn't take very long for these little rats and mice to reproduce. So they'll have a whole group of them, and they can do experiments with them on different drugs that you can't do on humans. So the research that's being done with animals is highly productive in helping us understand our own brain because they're a lot alike. So basically, what they've discovered is that each hemisphere of your brain has 4 major lobes. All right. Frontal lobes control what? Just told you. It's not that far gone. Higher level thinking, language, okay? Ability to feel your emotions, be aware of your emotions. The sides of your brain, remember what we said the sides of your brain control? Ability to hear, okay? Back of the brain, vision, good. And we didn't talk about this one, and they're called the parietal lobes. These are the lobes that take in sensory information, let you know whether it's too cold in the room, how your clothes feel on your body, whether it's pain or pressure, all right? So each lobe is covered with cortex. So we call the cortex covering the back of the brain the visual cortex, the auditory cortex, and the association cortex, because that's where you have a lot of your associations stored. Okay, this is another PET scan. And this time we're looking down on top of 2 brains. In yours, which is in black and white, it's kind of hard to see. But in a PET scan, the part of the brain that is most active shows up in white, then red, then yellow, then blues, greens, and purples, just like the rainbow. Okay, the colors in the rainbow. So we're looking down on top of 2 brains. The visual part of the brain's back here. Okay, frontal lobes are up here. The part that allows you to hear, the auditory is on the sides. And what is this across the middle of your brain? Motor cortex, very good. All right, now, take a look at these 2 brains. One of them is working a lot harder than the other one. One's using up a lot more glucose. Which one's working the hardest, right or left? Left, very good. How do you know that? See, you've already learned how to read a PET scan. Good for you. Okay, you see more activity. You see more yellow, you see more red. All right, now let me tell you that these are 2 boys. They are matched as carefully as you can match 2 people. Same age, obviously same gender, same IQ, same learning style, and they are both doing exactly the same thing. They are playing a computer game. Now, why is one of them, especially in this motor cortex, having to work so much harder than the other one? What do you think?
Because it's new to him.
Pardon?
Because it's new to him.
You bet. One is an expert and one is a novice. Which one is the expert? The one on the right. See, this is what's absolutely amazing about the human brain. You change it as you learn. Genes play an important part in who you are. They determine your height, your eye color, your basic personality style. But you don't have enough genes when you're born to determine who you're going to turn out to be. Your environment plays a huge role. So if I've never played a computer game, my brain is different from a person who plays it all the time. If I've never learned to play the piano, my brain is different than a concert pianist. If I never learned to drive, my brain is different than a cab driver. Environment changes the brain. We'll talk more about that in just a minute. We're not going to spend a lot of time on this, but I just want to tell you that your brain is made up of cells. And they're called neurons, which is Greek for stringy thing. Are they stringy? Yeah. And what these neurons have little connections on them. They're called dendrites. And they connect. They make connections. And your memory, your ability to learn, is contained in connections between these cells, which are called synapses. You've heard of synapses? Yeah. And it is both an electrical and a chemical process. You have over 100 different chemicals in your brain that your brain uses to connect these cells. You've already started hearing about them. Have you heard of dopamine, serotonin, endorphins? They're chemicals that the brain produces. And of course, when we take drugs, and put things in our bodies that it can mess up this connection between them, but that's another workshop. Okay, you have about 100 billion of these cells in your brain, these neurons. That's a lot. If you have 100 billion of them, and they only make up 10% of your brain, some other cells make up the rest of your brain, what's one thing you know about these cells? 100 billion of them. They're tiny. 30,000 of them would fit on the head of a pin. And yet, with today's technology, with electron microscopes, we know what they look like. And you can literally, in a rat brain, watch them making connections. That's why we know what we know. Okay, so what is learning? When you say you learn something, what is learning? Well, learning is the act of making and strengthening connections between brain cells. That's what it is. As you learn something, you literally sprout new connections. You make new connections as you learn. Now, do you think those connections will stay your whole life? How many of you took a foreign language in high school? How many of you speak it fluently today? One. Do you teach it? So did you continue to use it? Ah, there's the secret. Your brain is a loser, use it. So you can make these connections, all kinds of them, but if you don't use them, what do you think they do? The brain prunes them away. So learning is a matter of making and strengthening, continuing to use connections. If you don't use the connections, the brain says we're getting rid of them. We don't have room to keep connections you're not going to use. It's why you don't remember what happened in your high school chemistry class, or history, or that foreign language. All right? So what is memory? Well, it's the same thing. Memory is the ability to reactivate connections, but if you never use them, you can't reactivate them. All right? So learning and memory are inextricably linked. If you didn't learn it well enough and continue to practice it, it's gone, and you say your memory's gone. All right? So what these scientists are very fond of saying, this is the mantra of all your brain researchers, is that neurons that fire together, wire together. Now, they don't really wire together, but what are they saying? You've got to continue to use it if you want the connections to stay. All right? And so when we talk about kids in school, learning something for a test, and then as soon as the test is over, it's gone. One of the things we need to do is to keep coming back to it. Your memory. Okay, I took chemistry in high school, and I made an A. And all I remember is the boy who sat behind me, because he was really cute. And his name was Godfrey. I don't know why anyone named a child Godfrey, but they did. And he used to tap me on the shoulder, and he'd say, "You make my heart go pitter, Pat." Really corny. But you will notice that I remember his exact words, and nothing from chemistry. Memory is the ability to reactivate the connections you've made and used. I kept that. He was cute. He said something to me, that I want to remember, and I do. Okay. Now, this is a picture of learning. This is probably one of the sets of most amazing. This is human brain tissue from the cortex of the brain. These are those brain cells, okay? This is a newborn. This is a 2-year-old. Do they learn anything in the first 2 years? More than they will ever learn again, all right? There's a problem here, though. 2-year-olds have too many connections. They've made too many. It's called the terrible twos, okay? Now, what do you think the brain's going to do here? It's going to start pruning away some connections and making a more efficient brain. But it takes 2 or 3 years. So the terrible twos become the terrible threes, become the fearsome fours. And then by 5, the brain has pruned away, and you've got a much more efficient brain, and that's why we generally start kindergarten at 5. All right, they are ready. Okay, we're going to stop for just a minute. And I would like everyone in the room to get a partner, please, preferably someone sitting next to you. Don't move around. And decide which one of you is A and which one's B. And if you don't have a partner, raise your hand and we'll try and find you one. Because everyone needs a partner. Okay, you don't have a partner. Oh, okay, she's going to come be your partner. Okay. Okay, does everyone have a partner? Did you decide who's A and who's B? Okay, that's not the activity. There's more. Raise your hand if you're the B. You're working first. Listen carefully. We have been in session 40 minutes. All right? I want you to pretend your partner A just walked in the door. Missed the first 40 minutes. You will have 3 minutes. I'd like you to pick what you think are the most important things you've learned about the brain. What did A miss? What does A really need to know? And I'd like you to teach it to A in the next 3 minutes. You may use, of course, your handouts. Okay, your 3 minutes are up. So why did I ask you to do that? Why did I ask you to teach something to someone who's sitting right beside you, who's listening? You increased your memory. You increased your memory. Because what happens is that the synapse, between 2 cells, little chemicals flow. That's how you connect one brain cell to another. And the first time you learn something, say, a brand new term, maybe, I don't know, parietal lobe. It would take quite a little bit of chemical to make that connection. The second time it takes less. And the third time it takes less. You have strengthened the connection by teaching it to someone else. The more you repeat the information, the more you work with it, the stronger the connection. All right? So that's why the scientists say neurons that fire together wire together. The more you wire them. The more modalities you use to get information into your brain, the more avenues you have to retrieve it, the stronger the memory. It's not just repetition. Actually, you didn't just repeat. In fact, I can tell you that different people taught different things in the room. You didn't all teach the same thing in 3 minutes. Because I said, what do you think is the most important? Well, some of you think one thing is the most important, some another. Why would you do that? Why didn't everybody think the same things were important? You all have different experiences. What's going to be really important to one person is not going to be important to another. And incidentally, I'm afraid that's the way classrooms are. There's no such thing as a homogeneous classroom. They're all heterogeneous. Because, humor me, hold up your thumbs a minute. What do you know about the thumbprints in this room? So is every brain. Every brain is as unique as its thumbprint. Even identical twins who have exactly the same DNA in every cell. The egg split, they are, exactly the same. By the time they're born, they're already different. All right, because they were in a different place in the womb. A very interesting little piece of trivia. only about less than 5% of the population of the world is left-handed. Right-handedness appears to be the norm, all right? But in twins, you have a much higher incidence of left-handedness in one twin, but not the other. Even if they were both genetically programmed to be right-handed, one of them is born left-handed. What would that be? If my right arm is up against my twin and I can't move it, but I can move the left, the brain just switches me. It makes me a left-handed. Now, that's not the reason for all left-handedness, obviously, because not every left-handed person is a twin. But it shows you that your brain changes based on its environment. It's a plastic brain. Okay, so that's the first finding, and probably one of the most important findings of the brain. Experience sculpts the brain, both positively and negatively. And the term you want to remember is neuroplasticity. Neuro means mind, plasticity means malleable. All right? Now, you can change your brain, obviously, by overdosing on drugs. But I'm not talking about anything that, like that. I'm just saying that whether you heard 2 languages before you were born, before you were 5, and you are bilingual, that's a different brain. You have the ability to do that. You have a plastic brain. But if I'm raised as I was in an entirely English-speaking environment, then I'm not bilingual. Right? So your brain can change based. It's a wonderful, wonderful ability of the brain to change. Some examples. When a child is born, any child, anywhere in the entire world, already hardwired into the brain is the ability to hear the sounds, what we call phonemes, of every language in the world. You can hear, babies can hear them and they can pronounce them. But what happens? The sounds you hear over and over and over are going to strengthen certain connections. And the sounds you do not hear, what happens to those connections? They fade away. And by adolescence, they're all gone. And this is why it is so difficult to learn a second language as an adult. And why it is highly unlikely you can speak it without an accent. You can learn a second language as an adult, but it's going to be a lot of work. Is it a lot of work for little kids? No. They pick it up like you wouldn't believe. And the younger, the better.
Does it change their brain?
Pardon?
Does it change their brain to learn it before 6?
Does it change their brain? No, it activates a part of their brain that would not normally be activated. Actually, there are many cognitive benefits to being bilingual. Yeah. Bilingual individuals, I won't go through it, but there's a whole list of things they do better than monolinguals. Probably because they have to switch back and forth between languages all the time. They pay closer attention in school, if you're bilingual. I won't go into that, but there are many, many benefits to being bilingual. All right. All right, what do you think? This is probably one of the prime examples that people remember. Back here in the back of your brain, where vision is, you have 300 million brain cells. What would happen to the brain cells if you're born blind? You think they'd atrophy. They're not used. Use it or lose a brain? They don't. They literally change their function. They become auditory cells and tactile cells. If I'm not going to be used to see, I'll be used for something else. This is why people who are born blind have more acute hearing and tactile sensation. And I just heard a couple of years ago, Dr. Helen Nevels at the University of Oregon, who's working with people who are born deaf, and has discovered that they have better peripheral vision than the rest of us. All right. So here's, you got this brain. It says, okay, if I'm not going to be used for this, I'll be used for something else. This is plasticity. This is amazing. It is a feature of every brain all through life, yes.
Is that the same if you're an adult and you become blind?
Pardon?
Is that the same if you're an adult and you become blind?
No. Now, if you're an adult and you become blind, you will get some increased hearing and tactile sensation because you have to use them more to get around. And that's exactly what we're saying. Young brains are much more plastic than older brains, but you have plasticity your whole life. If you're interested in this, and it's a fascinating subject, there's a great book out called The Brain That Changes Itself. The Brain That Changes Itself. And it looks at stroke victims and some of the work they're doing in people getting back the use of arms or part of the body that the stroke had affected years after the stroke, when we thought it was no longer possible. So you've got an amazing brain. Got an amazing brain. So that's the first one. Experience literally shapes the brain. Now it can shape it negatively. If you take probably the worst example, or the best example of the worst case scenario, is Romanian orphans. And they are basically warehoused in cribs up until they're about 3. They're only out 1 hour a day. Now they're well fed, they're kept clean, they're cared for, but they are never allowed to bond with a caregiver because they're not held, they're not touched. And what they're finding is that the majority of these children, even when they're adopted into wonderful homes and given the very best of everything, have lost the ability to form healthy, intimate, emotional relationships with other people. The second finding about the brain, and this deals mostly with the ability to learn something new, what we're talking about in schools, is you have to realize that the brain doesn't hang on to information unless it makes sense. Okay? Our species has not evolved to the place where it is by taking in meaningless information and storing it. It just doesn't work that way. And this is why, you know, kids do well on a test and then 2 days later have no idea. You know, when I taught middle school, which I did for a very short period of time, the day I'm giving a test, kids stand outside the door till the bell rings. They wouldn't come in. As soon as the bell rings, they come bursting into the room saying, "Mrs. Wolf, just give us a test quick, don't talk." Well, see, they'd memorize this information. Outside, if I started talking, it was gone. Didn't make sense. So when you are trying to learn something new, your brain tries to hook it to something you already know. That's how you make sense out of things. What do I already know that helps me understand this? If it can't find anything you already know to hook it to, guess what? It is, what's the opposite of sense? Nonsense. And it will not be stored after the test. Here's an example. What do you see? A dog, very good. What kind of a dog? Dalmatian. Does everyone see the Dalmatian? Be honest. No. Well, if this is a classroom, you know what I'd say to you? You need to look harder. Oh yeah. You would be amazed at what people will see in this. I used to do a lot of work in Iowa, and they always saw a pig. Right there. See? Ears, snout. Okay. And then in Los Angeles, for some unknown reason, this is the beach. And then we have a cow here. One eye here, nose and mouth. Yeah. Except it's none of those things. But you see, what your brain is doing is trying to make sense out of it based on what you already know. People in California do not see pigs. People in Iowa do. Okay, they've got more networks in their brain, more experience than about pigs, and that's why they see it. Okay, let me help those of you who don't see it. Okay, does that help? Collar, ear, dog sniffing the ground. That's his back, it's his belly, leg. You see half of him? If this doesn't help, sorry. Okay, but I want to make a point here. Let's say I'm trying to teach you a new concept, and you have just arrived here from another planet. And so let's say I'm trying to teach Dalmatian today, and you came from a planet where they don't have any animals. Will you see the dog? No. What if I draw around it for you? No, it'd just be a lump. What if I have you do an internet search and write a report on Dalmatians? No. What am I going to have to do if I want you to understand Dalmatian? Bring the dog into the room. And this is just what you're saying. Why would bringing a dog into the room work better than just telling you about it or showing you pictures, better pictures than this of Dalmatians? Yeah. Can you smell the dog? You bet. Can you see the dog? Can you hear the dog bark? Can you feel the dog, its fur, its tongue? Okay. The more places in the brain you put that information, the stronger the memory. But if we do what you're doing here tonight, you just sit and listen to me talk, it's only getting into your brain one way, through the ears. Okay? And see, if we had several days, you would have to act out things. You would have to make up songs about the brain. We would do all kinds of things like that to strengthen you. This is just an introduction, okay? So if you want information to be meaningful, you have two choices. And the first one is you use analogies or metaphors or similes, and you say to the kids, this is like something you already know. It's my belief that every child comes to kindergarten already knowing how to add, subtract, multiply, and divide. They don't know the terms, and they don't know how to do it on paper. But I can tell you when my daughter was 4 and her brother was 2, I could give her a cookie and say, Andrea, I'd like you to divide this cookie equally with Tom. And he gets first choice. Could she divide equally? To the crumb. Okay. So what we need to do is when we're teaching new concepts, I watched a teacher teaching ratio not long ago. Ratio, that in 5th grade, that's a foreign word if there ever was one. She brings in a can of frozen orange juice. How do we mix it, she said. The kid said you mix 3 cans of water to 1 can of concentrate, she says. That's all it is. It's a ratio. How much of one to how much of another? What else can you think of? And the kids are ratio of boys to girls, ratio of, they had it already. Not giving them the dictionary definition, finding something they already knew and giving them the word for it. This is what we call it in school. This is what we call it in school. If you can't find the experience they've already had, then you better create it. Bring the dog into the room. This is why hands-on instruction, why field trips, are so critical. That's how you build. We'll just skip that. Can you make very good grades even without understanding the information? Let's find out. I would like you all to read this paragraph called The Montylation of Traxylene, and then we're going to have a test. Okay, you've had plenty of time to read that. What is traxylene? New form of Zienter, very good. And where's it montyled? Excellent, you are doing, class, you are paying very close attention, I can tell. I really appreciate that. And be careful, the next question has a 2-part answer. How do you quassel traxylene? What do you do first, and what do you do second? First, you're going to glycerate it with what? Extra points if you can tell me what you glycerate it with. Fivon, very good. And then what do you do to it? Excellent. Class, I would not be giving this to you if it were not extremely important. Why is it important for you to know about traxylene? Because it's on the standardized test. Okay. Now, you all just made an A. What kind of neural connections do you think that just made? 0. Did any of you ever take a course in traxylene? Yes. Yes, it was called statistics. Yes. Anything that doesn't make sense to kids is just like this. And they try and memorize it with no understanding. I had a whole bunch of courses in traxylene. Okay. 3rd point, major finding from the brain. Emotions are really important for learning. And emotions can impact learning in one of 2 ways. It's kind of a double-edged sword, negatively or positively. So first, let's look at the negative part. What happens when you perceive a situation to be really threatening? Somebody comes at you with a gun, or a dog comes snarling at you while you're riding your bike. You go into what is called fight or flight. Okay. And when you go into fight or flight, chemicals are released throughout your whole body. It's ancient. It's ancient. It was our ancestors' brains when they lived out on savannas because they were being chased by wild beasts. So it hasn't changed. We just don't face a lot of wild beasts, but the whole system hasn't changed. So any situation you perceive to be threatening causes your body to go into this fight or flight response. Adrenaline, cortisol are released in your body. Your heart starts beating faster, your lungs produce more oxygen to allow you to run, you get more glucose coming out from the liver to increase strength, all right? People have been known to lift cars in fight or flight. But the problem is, while that might save your life, okay, the brain doesn't distinguish between physical threat and psychological threat. We go into fight or flight when somebody insults us. All right? We go into fight or flight in perceived situations where there was no threat involved at all. Have you ever been scared when there was nothing there? You hear these noises, you know, all right? And if a student thinks they're not going to do well on a test, they go into fight or flight and can remember nothing. Because what happens in the frontal lobes of the brain, when you go into fight or flight, the frontal lobes quit working. Have you ever been insulted and could not think of a retort till the next day? It's a perfect example. The part of the brain that's thinking up clever retorts isn't working when you're in fight or flight. Have you ever been so angry you didn't think rationally? Oh, yeah. Have you ever been so happy you didn't think rationally? That's called getting married. Joking, okay. So that's the negative part, all right? So a classroom or any situation has to be psychologically safe as well as physically safe. If I feel threatened, and incidentally, if you look at the list, it's been People's Almanac had this list of things people fear the most in life in today's culture. What's at the top of the list? Public speaking. Death is number 7. Doesn't have to be a real threat. You know, Seinfeld had a lot of fun with that on one episode. He says, you mean, if you're at a funeral, you'd rather be in the box than give the eulogy? We're not rational. Okay. All right. However, anything with strong emotion in it is remembered longer, period. It's why you remember your first kiss, but not the 35th. Yeah. It's why you remember when the Challenger exploded, but not all the other launches. All right. It's why you remember when Princess Diana was killed. It's why you remember what happened yesterday with Osama bin Laden. These things stick because of high emotion. So when in classrooms, teachers do things that are highly motivating, having the kids, I watch kids acting out World War I. Now, how do you do that? They're sitting in trenches, which are chairs turned upside down. They're sitting on the floor in these trenches. There's a DVD playing on the screen of bombing, and they are writing letters home, telling it what it's like to be in the trenches in World War I. Do you think they will remember that longer than reading about it in a textbook? Yes. Oh, yeah. Oh, yeah. You want kids to learn, and with your own family, you want kids to learn, and you want, stress is good, a certain amount of it. But if it gets too high, what happens? You shut down learning. See, if there's no stress in my life, I don't get out of bed in the morning. Okay? And if there's too much stress in my life, I don't get out of bed in the morning. So this balance of the right amount of stress, but not too much, okay, is really important. Number 4, and this is a really interesting one and a very important one. There are 2 very different types of memory, and they use different brain structures, all right? And one type of memory is called procedural memory. And it's where you program your brain, especially this motor strip, okay? When you do something over and over and over and over, pretty soon the brain remembers how to do it without your even thinking about it. It's called procedural memory. A procedure, a memory for a procedure that has become automatic and unconscious. How many of you drive your car to work pretty much the same way every day? How many of you have driven there and all of a sudden realize you're not aware of having driven there? That's procedural memory. What else do you have at that level? Something you've learned to do that you've done so much that it's now automatic and unconscious. You don't even have to think about it. Tying your shoes. Pardon? Flushing the toilet, yeah. How about the seatbelt? It just has become almost totally, for most people, automatic. Brushing your teeth. Athletes must have a lot of their skill at the automatic level. Musicians, you'll never get to be a concert pianist unless you have totally memorized that piece and the fingers know where to go, or the part of the brain that tells the fingers where to go. All right. So in schools or with kids, there are certain things we want to get to this level, like behaviors, like saying thank you, all right, like pushing in your chair, like taking your dishes over to the dishwasher when you're through. I mean, could name a million of those. To do them over and over and over and reinforce kids doing it so that they become automatic. In the classroom, you want your rules and procedures here. Unfortunately, we don't practice them enough so they get there, but that's what you'd like. All right. But there's another, yes?
Is that why the picture of the two brains, is that why the one boy didn't have to work as hard to play the video game as the other boy?
Because he practiced more, he had more of it at the,
He wasn't
yes,
thinking about it.
precisely. He was either moving a joystick or whatever, you know, that particular game called for. He'd done it so much it was automatic, he didn't even have to look down at the keys. How about people who type, who learned to type without, you know, looking? Until you get to a number, and then you have to look. Okay, yeah. And so you're just sitting there. That's procedural memory. Good examples. In fact, if you ask Tiger Woods, you know, how to swing a golf club, he can't tell you. He doesn't know anymore. It's totally automatic. You have to watch him and try and figure it out. This is true for all athletes or musicians. How do they get there? They don't know anymore, all right, because it's unconscious. Okay. Now, the second type of memory is called declarative memory, and this is what we usually think about when we think of memory, like, you know, what someone's name is, what street you live on, what's 6 times 7, you know, all of it's what we teach in schools, your concepts and dates, and the episodes of your life. This is declarative. They're things you can declare, not how to do something. And interestingly enough, they use different brain structures. Now, the reason this is included for teachers is that if you want to get something to the automatic level, like driving a car, rote rehearsal. You drive the car over and over and over and over in the same way. You don't want creative car driving, okay? Right. Go to kids writing. I'm watching, you know, my grandchildren who are 6 in kindergarten, laboriously, you know, which way does the bee go, Grandma? You know, pretty soon you don't have to think which way the bee goes, but you're going to have to write that bee, you know, hundreds of times versus the D, you know, before that becomes automatic. And reading, they've got to read and read and read. You know, you have that at the procedural level. If you read a page in a book, get to the bottom of the page and have no idea what you just read, it's automatic. Your brain went right ahead and decoded every word on the page. It was unconscious. So that's what you need to do. But if we are teaching concepts, rote rehearsal doesn't work well. And that's when you need to look at elaborating on it, all right? Can you act out how neurons connect? You know, can you make up a song? And oh, I have some great ones because I do 4- and 5-day workshops where the participants have to make up songs to help them remember parts of the brain. Okay, you know, and they do it to the tune of what's it from? It's because I have a brain. Yeah, the Wizard of Oz. Yeah. So this is what we call elaborative rehearsal. Finding analogies, finding metaphors, things that are similar. Having kids solve problems using what they've learned in multiplication. You know, not just being able to multiply, but how do you solve this problem? Do you use multiplication? Do you use division, addition, subtraction? Having kids draw pictures of what they've learned. This is why graphs and all the visuals, the brain loves visuals, remembers pictures much longer than words. Hands-on activities. And rhythm, rhyme, and rap. Yes?
What makes someone more of a visual learner or more of an audio learner?
Actually, I do not believe that that we have visual learners, kinesthetic learners, and auditory learners. First of all, 76% of all the sensory receptors in the brain are for vision. We are primarily visual. Now, it is true that some people have trained themselves to listen better than others have. But I don't believe we should ever be testing kids for whether they're visual or auditory or kinesthetic and then trying to match. I think you should give kids lots of opportunities for all three. Yeah, I think they need to act out things. Am I coming and going? Yeah.
Stay right there.
I'm just going to sit. Okay. Okay, and then, before we get to the end piece on some of the new stuff, this is relatively new. Consolidation. Consolidation. And what this means is that when you learn something, it is not well established immediately. It takes time to gel or to set. Think of Jell-O. Anybody ever made Jell-O? So that's going to move it from short-term memory to long-term memory. And it takes time. All right? So new information is not fixed the moment it's processed. So I might have the answer for you right now, and the next day, this is why you can teach something one day and the next day kids act as if they've never heard it. It didn't get gelled. So what they've discovered is that we need to come back to things and back to them and back to them and back to them. So it's like massed practice in the beginning, lots of opportunities to go over it, to teach it to someone else, to write about it, to make up a song, etc. But then you don't just drop it. You know, a week later you're going to come back to it, and then back to it. So it's masked at the beginning and then distributed. So here's probably the best example. They took these fish, and fish do have brains. They're little, but they have brains. So they take all these fish and they put them in this tank, all right? And there's a net in the middle of the tank, and it's electrified. And if the fish swim into the net, they shock their little noses. So it doesn't take long for them to learn not to swim into the net. And all the fish have learned it. Okay, now we take all the fish out of the tank and we divide them in half. Half of them go into a tank where they just get to swim. They don't have to learn anything new for a while. The other half put into a tank where they have to learn something new. Now let's put them all back in the first tank, and what happens? The fish who had time to consolidate their learning, just to swim back and forth, were fine. They didn't swim into the net. But when we had taught two things too close together to the other fish, they forgot the first thing and swam right back into the net. Now, this is going ahead, but when does most consolidation take place in the brain? When you're asleep. Yeah, when you're asleep. Your brain rehearses what you've learned during the day while you sleep. So, let's see. Okay, I'm going to come back to that in just a minute. I've got these out of order. So this is some of the new things that we've learned in the last 4 or 5 years, is that exercise increases the potential for learning. Number one, it needs to be aerobic. You need to get your heart rate up. It increases oxygen flow to the brain. The more oxygen you've got in your brain, the better. All right? And there's this factor called BDNF, the brain-derived neurotropic factor, which you probably don't have to remember. But it is something that stimulates brain cells and helps them make better connections. There's a whole book out on this. Yeah. The book is called Spark, on the research on exercise in the brain. And John Rady, the author, calls this BDNF miracle grow for the brain. Miracle grow for the brain. In other words, there's an actual chemical change that occurs in the brain with aerobic exercise that increases the connections between cells and strengthens learning. Also, some relatively new research is it used to be thought that you had all of your neurons at birth and you never grew anymore. Now they found that there's 2 places in the brain where you do grow some new cells. One is in the olfactory system, and the other is in a part of the brain called the hippocampus, which helps you establish memory. And they've discovered that exercise increases new cells in the brain. And everybody would like to have new cells, all right? So when students, in Rady's book, Spark, gives a lot of examples. Like they took two groups of kids and matched them very, very carefully, which you always do when you're going to have a good research study. Okay, you have a control and experimental, but they're all alike, as close as you get. One group of kids ran the track 4 or 5 times before they took a math test. Both groups had the same instruction with the same teacher. The other kids didn't. These kids outscored the others tremendously. More oxygen to the brain. And for those of us who are getting into our golden years, they have discovered that probably the one factor, if you could do one thing to decrease the probability that you get Alzheimer's, it's exercise. We're seeing more and more and more research coming out on that. You know, and none of us like it. Okay? Very few of us like it. All right. But it is a critical factor. Technology. Technology, this is new, and we're going to be learning a lot. It's not clear cut. It's not black and white. They're both positive and negative. Okay, so because we have neuroplasticity, right, it's obvious that technology is going to be changing the brain. How it's changing the brain, we're not sure. How does cell phone use? Yeah, I was driving today from Vallejo, back up here to Napa, and I'm looking in cars, even though it's against the law. Half of the people I looked at had cell phones to their ears. And then you look out at the people on the street, and then the horrible one was this kid on a bicycle ran right through a red light in an intersection, driving with no hands because he had a cell phone on this ear, and he had to take out his plugs from his iPod with the other. And he's driving with his knees. Now, that's got to be changing the brain. All right, but what research is there out there? Okay, there are computer games that very definitely enhance learning and correct some brain deficits. Brainware Safari and Fast Forward are two of the programs that I'm familiar with that have very positive aspect. Fast Forward helps kids who have an auditory processing delay, who have difficulty blending sounds together so they can't read. A lot of good research in correcting that. That computer game literally changes their brains, the auditory processing, to normal speed. Brainware Safari addresses 41 different cognitive skills. Let's take television programs. There was one book out, he said, if you take a look at the content of, now I don't have a TV, so I don't know, but sometimes when I'm in hotels I watch, let me take that back. I have a television set. I don't have cable, so it never gets turned on. Okay, the kids watch DVDs on it, all right. But every once in a while I'm on a trip in a hotel, I turn it on and then usually turn it right back off again. But if you look at the programs today, especially the long-running ones, they are much more complex than anything we watched when we were younger. Those super soupy programs we watched where the mother and father were wonderful and the kids got into little scrapes like, nothing like, There's some research or some researchers who believe that following the plot of some of these television programs today is actually enhancing the brain to recall information and might have some positive benefits, all right? So some television, now, and there are also television programs like, Electric Company, the new Electric Company, very good program. Although, what about Baby Einstein? Big study. Toddlers, the little ones, who watched an hour of Baby Einstein a day had lower vocabulary than kids who didn't. So you never know, yeah.
Would not be because it's not a three-dimensional experience? They're just watching
What's really interesting? If you look at the research on learning a second language, people say, well, okay, being bilingual has big benefits. I'm going to play French tapes for my kids. You don't learn them. You've got to watch the face. They're watching, kids are watching your mouth, they're watching your tongue, they're watching your teeth. From the time they're born, they are watching. They are actually beginning to practice language long before they speak. And television doesn't do that. You need the one-to-one interaction. yeah, for that. This one was interesting. Excessive playing of violent video games. What do you think it does? It appears to desensitize the brain to violence. That's scary. That's scary, you know. So what most of us would really recoil at, the people who play extensively these violent games don't. That's not a positive change. Here again, the bottom line on technology in the brain, it depends. Depends on the person's brain, depends on the person's home family, it depends on how much time they're spending on it, depends on whether it's a program. There are a lot of computer programs that help kids learn. I know at my grandkids' school, everybody goes to the computer lab every day, but it's very specialized what they're doing and very geared to the different age groups. Problem solving. There was a big study done in Chicago on use of computers to learn mathematics. And what they discovered was that if you just use the computers as dittos, you know, they're just worksheets, like they're just computerized worksheets, didn't help. But if they use the computers in math to solve problems using what they've learned in math, huge gains. So here again, it's how it is used.
So Pat, research shows that children under the age of 2 ought not to watch television.
Most people believe that children under the age of 2 should not be watching television and should not be on a computer.
Okay. Can you talk a little bit about that? And then I just recently heard that now they're saying before the age of 4.
Well, here again, it depends on what television and how long. So for example, with the twins, I believe strongly that you should teach children to sign before they can talk. It reduces your frustration and the kids' frustration, okay? So we started them, even before they were 2, watching this signing video. And sure enough, they picked it up really, really fast. But it was 20 minutes a day. Now, you know, if you look at the experts, they say no television before 2. Well, what are they talking about? If you use the television for a babysitter, it's really bad. If they're sitting there for long periods of time and you're not monitoring it. But if you're sitting there with them, doing things with them, and the program is a good program, that's why I say it's not black and white. You know, every time you try and put numbers on things, you run into trouble. Yeah, an awful lot depends. Okay, and now the sleep plays an important role in consolidation. Our culture seems to think it's, we brag about how much sleep we can get by with, how little sleep we can get by with, all right? And we kind of have so much to do if we could just squeeze in an extra hour. But quite the opposite is true. You know, it might appear that your brain is not doing a thing while you're asleep. But you know what an EEG, electroencephalogram, does? They put electrodes on your head and you get brain waves. Okay, you have different kinds of brain waves. You have slow ones, you have spiky ones. When you go into what is called REM sleep, very deep sleep every 90 minutes, your brain waves are as active as if you are awake solving a complex problem. Sleep is essential, right? The brain not only rebuilds its cells, it also rehearses information.
Is it REM sleep when you're coming out and dreaming, not when you're in deep sleep?
It's mostly in your deepest dreaming sleep, what they call REM sleep, that most of the consolidation appears to take place. So like every 90 minutes, you know, you go down, 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 you go into really deep REM sleep. When you go into deep, it's called rapid eye movement. Watch a dog or a cat sleeping, you can watch their eyes do it. Yours do it too. You don't know that because you're asleep. Yeah, but it's during that sleep that the brain waves really spike like you're solving problems. That appears. So here, let me make it clear. Take 2 groups of people, put them in a sleep lab. They all have the electrodes on them. And they're matched. One group of people, you wake up every time they go into REM sleep, so they can't dream. Then they're allowed to go back to sleep. 90 minutes later, wake them up again. 90 minutes later, wake them up again all night. The other group, they woke up the same number of times, but during non-REM sleep. Now, they had given them all a group of new words that they'd learned before they went to sleep. The next morning, the people who had been allowed to dream remembered 50% more than the people who had not. It's really a lot of good research. Sleep is essential. How much sleep? Oops, wrong button. Okay, you're just going to watch it this way. Oh, well, I guess I'm going to see it. This is a picture of my grandchildren, which is what I'm ending with. Okay, elementary kids, 10 to 12 hours. Adolescents, 9 3/4. And all of you, 7.5 to 8, at least.
They say before midnight is the best sleep. Is that true or is that another myth?
It's another myth. Yeah, yeah.
Could you repeat those figures
Yes.
again?
10 to 12 for elementary children. 9 3/4 for adolescents who don't get it.
And adolescence is from 12 to 25?
12 to 25. For their brain to function optimally. Don't try and convince your teenager of it. It will work. And for adults, 7.5 to 8.
And before 10?
Well, that's another thing. All of you in this room, you have these, it's called circadian rhythms, your brain, the cycles, okay? You get sleepy between 10 and 11, most of us, okay, unless you've got yourself programmed in something else, and wake up between 6 and 7. Adolescent sleep cycles are programmed later in the brain. They do not get sleepy until 11 to 12.
I meant before 10 years old.
That's after 10. Between 11 and 12 and 25, the sleep cycle changes later than it will be as an adult or than it was in elementary. And then we have high school classes that start at 7:30. That make any sense. And some schools have tried to change that, but the coaches and the bus drivers vetoed it. Because they were practicing too late. Okay, we're not through. A's, if you've forgotten who you are, ask B. It's your turn. Okay, since B taught you, pick out what you think are 2 or 3 of the most important things you learned and teach them to B now. Which, of course, is a lot harder. Our time is up. Let me just tell you really briefly. Okay, thank you. I would like us to get rid of the phrase, I like the way that. So when you say to a child, oh, I really like the way you cleaned up your room. Or I really like the way this table is sitting. I really like that test. What you are doing is we're making praise junkies out of kids. So then they're doing it to please you because I like. So pretty soon they start coming to you and say, how do you like this?
Right.
Is it okay? We're making praise junkies out of them. What praise should do is to help encourage them and build, I like to call it an inner locus of control. Let me give you some examples. Instead of, I like the way you cleaned up your room, try this. You have everything put away. You've got your clothes in the closet. Boy, what organization you have. Now the child can say, not my mom is pleased, I'm organized. See the difference? All right? Instead of, oh, I really like the way you stood up for your friend when everyone else was making fun of him. Try this. You stood up for your friend when everyone else was making fun of him. That is real loyalty. It may seem like a really subtle difference, but it's huge. It is huge. Get rid of the good jobs. Good job, good job, good job. That doesn't tell them a thing, except you liked it. Praise needs to be specific and let them know what they're doing. So for example, they've written a story. They get an A on their paper. You say to them, this story was really interesting to read. I could hardly wait till I got to the end to see what was going to happen. What's that say to the kid? I know how to write. I'm a good writer. Not my mom or my dad liked my paper. That's an entirely different, and they know you like it when you say that. But we overuse, good job, super, wonderful, fantastic, get rid of it. that also shows that if the child is already motivated to do something, you're praising them, breaks down the motivation. It decreases their motivation if they get too much praise. And when they're older, they don't like public praise. You know, the last thing on earth you would ever do in a middle school classroom is say, I really like that paper you wrote. Would you come up here and read it for the class? That is murder. Now, everyone's going to go, brown nose, you know, this whole thing. So what I would say is what you want to do is build autonomy and help the kids realize their own strengths and what they do that is well by labeling it for them, not just by telling them you like it. Okay, and the second thing, ton of research on this one. Do not praise kids for being smart. Praise them for effort. Now, there are some kids who are very, very bright. And, you know, we have a tendency to say, oh, you are so smart. What happens with these kids is that they kind of sail through and then they hit something they can't do. And if they have not been praised for effort, if they thought it was just their smarts, now they're not smart anymore. And they won't do it. So you want to say, it is obvious you really worked hard on this. Okay. I can tell the effort you put into this. You know, compare this paper with the one you did last week. Look how much improvement and progress you've made. Does this make any sense?
Yeah.
Okay.
They talk about that in the book, How We Decide.
Yeah, how we decide. I'll tell you, it's a hard, hard habit to break. I volunteer 2 mornings a week in the kindergarten classroom, and I work with Spanish-speaking children on their English vocabulary. And I find myself saying, why don't you say, good job? And I have to stop and say, no, don't do that. You know, sometimes all you have to do is smile, or nod, or give them a thumbs up. However, that's not specific. But when you can label, it wasn't easy, but you remembered to leave a finger space between every word, is all you need to say. Not, I like the way you remembered to leave. Try it. Try it. Makes all the difference in the world. Okay, you can go home.